Pick up a coffee cup sometime and just watch it. Really watch it. Pour a drop of cream into the dark liquid and observe what happens next. The cream doesn't stay in one place. It doesn't wait politely for instructions. It blooms outward in slow white ribbons, curling and spreading until the whole cup is a uniform shade of tan. That process takes maybe 30 seconds, and once it's done, it is done. You will never watch that coffee unseparate itself. You will never see the cream gather back into a single droplet and retreat to where it started. That simple fact, that unremarkable everyday observation, sits at the heart of one of the deepest ideas in all of physics. The universe has a direction, not a direction in space, like north or east, but a direction in time. Things move from ordered states toward disordered ones. Broken eggs don't unbreak. Smoke doesn't flow back into a cigarette. A shattered glass on a kitchen floor stays shattered. We all know this, somewhere in our bones, even if we've never put a name to it. The name, when it came, was entropy. And entropy, put simply, is a measure of disorder, a way of counting how many arrangements a system could be in while still looking roughly the same from the outside. Think about that coffee again. Before the cream spreads, the system is in a very specific state. Cream here, coffee there, a clean boundary between them. There aren't many ways to arrange the molecules and still get that picture. But after mixing, the molecules can be scrambled in an almost uncountable number of ways, and the cup would still look the same, just a uniform beige. More possible arrangements means higher entropy, and nature, as it turns out, is extraordinarily good at finding its way towards states that have more possible arrangements. This isn't a rule that nature enforces from the outside, like a speed limit. It emerges from pure probability. Disorder wins not because the universe prefers it in some philosophical sense, but because disordered states are so vastly more numerous than ordered ones. If you shuffled the molecules at random, you would almost never land on the precise configuration where the cream is neatly separated. You'd land on something mixed, because mixed is almost everything there is. That asymmetry, order giving way to disorder, almost always, almost everywhere, is what physicists call the second law of thermodynamics. It is the reason time feels like it flows in one direction. It is the arrow embedded in every cooling cup of coffee, every crumbling stone wall, every breath you exhale into the open air. And it is the thread we will follow through this entire book, not because entropy is grim or defeatist, but because understanding why disorder grows is, strangely, one of the most illuminating things a person can do. The universe is telling us something with every scattered drop of cream. We just have to learn how to listen. So, listening, it turns out, requires numbers. Ludwig Boltzmann understood this in a way that made him deeply unpopular with the physicists of his day. He believed that matter was made of atoms, which was still a contested idea in the late 19th century, and he believed that the behavior of those atoms, taken together, could explain the large-scale world we actually see. Not through mysticism, not through vague appeals to nature's tendencies, through counting. Here is the central idea. Imagine you have a small box divided down the middle, and inside it you have just 4 gas molecules. You remove the divider. Where do the molecules go? They can go anywhere. And if you ask how many different ways the molecules can arrange themselves with all 4 on the left side, the answer is exactly 1. All 4 on the left. That's it. But if you ask how many ways they can arrange themselves with 2 on each side, the answer is 6. 6 different arrangements all look the same from the outside. 2 left, 2 right. But underneath, at the microscopic level, the molecules are shuffled differently each time. This is what Boltzmann saw. Macroscopic states are not all equal. Some of them can be achieved in only one way. Others can be achieved in an enormous number of ways. And if the molecules are moving randomly, bouncing and jostling without any preference for left or right, then the states that can be achieved in more ways are simply more likely to occur. Not because something is pushing them there, just because there are more roads that lead to them. Entropy, then, is a measure of that number. The more microscopic arrangements that correspond to a given microscopic state, the higher the entropy of that state. Boltzmann captured this in a single equation, carved eventually onto his tombstone in Vienna. S equals K times the logarithm of W. S is entropy. W is the number of microscopic arrangements. The logarithm is there to make the numbers manageable, because W can grow to be almost incomprehensibly large. And K, the small constant bearing his name, ties the mathematics to the physical world we can measure. Now scale up from 4 molecules to the number of molecules in a real breath of air. We are talking about something like 10 to the power of 22 particles. The number of arrangements available to a disordered, spread-out gas compared to a neatly compressed one is not just bigger. It is bigger by a margin that has no meaningful analogy in everyday life. The ordered state is not impossible. It is just so vanishingly rare that in the lifetime of the universe, you would never expect to see it happen by chance. This is why disorder grows, not because the universe prefers it in any emotional sense, but because disorder is, in the most literal and mathematical way, overwhelmingly more probable. Order is a needle, disorder is the haystack, and the haystack always wins. And so we arrive at the deepest question of all. If disorder always wins, if entropy is the universe's relentless tendency, then what does that mean for time itself? Here is something remarkable. The laws of physics at the level of individual particles are almost perfectly symmetric in time. Run a video of 2 billiard balls colliding, then run it backwards. You cannot tell the difference. Both directions look equally valid. Nothing in the fundamental equations of motion says that time must flow forward. And yet it does. You age, coffee cools, eggs break, the past is fixed and the future is open. Something gives time its arrow, and that something is entropy. The second law of thermodynamics is, in a very real sense, the reason you experience time as moving in one direction. The universe began in an extraordinarily low entropy state. Extraordinarily ordered, extraordinarily improbable. And ever since that first moment, it has been climbing toward greater and greater disorder. We remember the past because it was more ordered. We cannot remember the future because it has not yet become the past. The arrow of entropy and the arrow of time are, at their roots, the same arrow. Follow that arrow far enough, and you arrive at a destination physicists call the heat death of the universe. Billions upon billions of years from now, if nothing interrupts the march of entropy, all the stars will have burned out, all matter will have decayed or dispersed. The temperature everywhere will be the same. No gradients, no differences, no work left to be done. The universe will have reached its maximum entropy, perfect, featureless equilibrium, a final, absolute stillness. It sounds bleak. But here is the thing. We should not mistake the destination for the journey. Right now, the universe is nowhere near that end. It is in the middle of a vast, glorious cascade of entropy production. And complexity, life, thought, these are not somehow opposed to entropy. They are its offspring. When energy flows downhill from order to disorder, it does not always do so quietly. Sometimes it does so through the most astonishing structures imaginable. A hurricane is entropy in motion, a flame is entropy made visible, and a living cell, metabolizing and reproducing and sensing its world, is entropy flowing through matter in its most breathtaking form yet. Life does not fight the second law. Life surfs it. So entropy is not the enemy of meaning. It is the source of it. Every thought you have, every heartbeat, every moment of beauty or grief or wonder, all of it is possible because the universe started ordered and is spending that order, slowly, magnificently, across cosmic time. The arrow is real. The direction is fixed, and we are alive, right now, in the brief and luminous middle of it all.